Welcome back. So far, we covered topic 1 and topic 2. With some practice, you're able to solve external flow convection problems. Now, it's time to review convection theory in topic 3. A. Definition of boundary layer. When a cold flow is passed over a hot stationary plate, the velocity boundary layer and the thermal boundary layer are formed on the solid surface. The thickness of the velocity boundary layer is represented by delta, and the thickness of the thermal boundary layer is represented by delta T. A boundary layer is a very thin layer next to the solid surface where the fluid velocity and temperature changes significantly. As a result, 99% of friction and 99% convection heat are generated within this thin boundary layer. From the condition for velocity boundary layer and for thermal boundary layer to exist, the Reynolds number must be very high. B. Understanding boundary layer. The definition of boundary layer is dry. Let's try to make some sense of it by asking a few questions. The first question is, why do we care about boundary layer when we study convection? The answer is that convection is all about heat exchange between the solid surface and the moving fluid. Whenever the temperature difference or the contacting area or the heat transfer coefficient is increased, the convection effect is enhanced. For convection study, we focused upon getting the H heat transfer coefficient value. The heat transfer coefficient H really represents the ability of the moving fluid carrying the heat rate to run around in the boundary layer region. You can imagine when the speed of the moving fluid is increased or the thickness of the boundary layer is reduced, more convection heat is delivered. Therefore, what happened in the boundary layer is closely associated with heat transfer coefficient and convection heat rate. That's why we care about boundary layer when we study convection. The second question is, why the boundary layer is formed on the solid surface? The answer is that you can think of the boundary layer as a cushion. When the coming fluid jumps to the solid object, a thin layer must be formed next to the object in such a way that within the boundary layer, a cushion, the fluid can make a realistic transition from the zero speed of the object to the speed of the incoming fluid and make a realistic transition from the temperature of the object to the temperature of the incoming fluid. Otherwise, it is impossible for this kind of a transition. The last question is, it appears that both velocity boundary layer and thermal boundary layer are formed on the same solid surface. It is true? The answer is yes. Then which boundary layer is thicker or thinner or the same? In order to answer this question, let's talk to Mr. Prandtl. See, Prandtl number. When the Prandtl number was first introduced, it was treated as a fluid property like conductivity and viscosity. Mathematically, the Prandtl number is defined as the ratio between viscosity mu and diffusivity alpha. It has no unit. The usefulness of Prandtl number is that it is a good indicator on how the boundary layer is related to each other. For example, if the Prandtl number is much less than 1, such as Prandtl number is 0.01, the heat diffuses more quickly in the fluid than momentum and friction. Therefore, the thermal boundary layer is much thicker. Here is an analogy to help you understand the Prandtl number better. You can think of the viscosity mu as the running speed of molecules carrying friction, and diffusivity alpha as the running speed of molecules carrying heat. If the Prandtl number is small, it indicates mu is small, alpha is large. Therefore, molecules carrying friction are running slowly, but molecules carrying heat are running much faster. Therefore, we have a thicker thermal boundary layer. Similarly, if Prandtl number is much greater than 1, such as Prandtl number is 100, heat diffuses very slowly, and therefore thermal boundary layer is much thinner compared to the velocity boundary layer. Finally, if the Prandtl number is close to 1, the thickness for the velocity boundary layer and for the thermal boundary layer is about the same. D. Nusselt number. Mathematically, a Nusselt number is a combination of heat transfer coefficient, characteristic lengths, and thermal conductivity of fluid, with a little math rearrangement. Nusselt number represents the ratio between convection heat rate and conduction heat rate. What does it mean by that? Here is an analogy to help illustrate the physical meaning of the Nusselt number. For case A, there's a conduction within the stationary fluid layer, due to the temperature difference. For case B, there's a convection within the moving fluid layer due to the temperature difference. On one hand, the conduction flow heat rate Q is like people carrying a bag of heat are walking slowly from Ts to T infinity. On the other hand, convection heat flow Q is like a large truck full of heat is driven fast from Ts to T infinity. Therefore, a big Nusselt number indicates that the heat transfer rate due to fluid motion is much stronger. There's a question related to Nusselt number, which is why do we have different Nusselt number equations, such as for our cylinder? Actually, there are two methods to evaluate heat transfer coefficient H. Method 1 is that if we know the temperature profile within the boundary layer, we can use equation 1 to find H value. Method 2 is that through dimensional analysis with experimental data, we can get empirical correlation for the Nusselt number like a 2, and then use equation 3 to get H value. With different dimensional analysis method and different experimental data, we may get different Nusselt number equations. Therefore, the predicted value of heat transfer coefficient H might be different. E. Fluid property. How to get it? What we have learned is that there are 4 fluid properties involved in the convection problems, and we can rate from the table to get property value. The question related is that which reference temperature is used to rate from table for the property values. It depends upon the flow topology. If it is external flow convection, we use the film temperature. If it is internal flow convection and we're looking for local heat transfer coefficient at location X, we use local flow temperature. Otherwise, if we're looking for averaged heat transfer coefficient, we use averaged flow temperature. F. Overall heat transfer coefficient, U, in the multiple heat transfer mode. This is a problem statement which is used to define the overall heat transfer coefficient. As you can see, a state heat rate through a 0.2 meter thick break with a wall area A and thermal conductivity K. One fluid is at temperature T infinity 1 and heat transfer coefficient H1. The other fluid is at temperature T infinity 2 and heat transfer coefficient H2. We need find heat rate through the brick and the overall heat transfer coefficient U. That's what we know and what we need to find out. Next, let's identify the heat transfer mode. We have convection between moving fluid 1 and a solid surface. There's conduction heat flow within the brick. We have another convection between a moving fluid 2 and solid surface. Next, we try to draw the thermal circuit with thermal resistance and heat flows. Since we know the temperature difference between T infinite 1 and infinite 2, and the three thermal resistance are in series, we can come up with equation 1 to calculate the heat rate through the brick, which is temperature difference divided by the summation over all three thermal resistance, and then it can be rewritten as delta T over RT total. Next, we introduce the overall heat transfer coefficient in equation 2, which is UA equals 1 over RT total. Then plug into equation 2 into equation 1, and it yields equation 3, which is really similar to the Newton's cooling law, UH area A, temperature difference. The reason we introduce overall heat transfer coefficient U is that this U value really indicates how good, how bad the heat is conducted through over a series of resistance mediums. It is widely used in the HVAC and construction or building areas. At this point, we covered topic 3, convection theory, on boundary layer, variables, and reference temperature for property reading. At this point, we finish chapter 6 and 7 with beautiful summary and outcomes on concepts, variables, scales, and equations. We end chapter 6 and 7.